Explosives, they're this fundamental force that has totally shaped our world, from literally carving mountains for our cities to defining the very nature of modern conflict. But what is actually happening in that split second of detonation? Well, today, we're going to unpack the incredible science behind these energetic materials. Let's dive right in. So this is the big question, right? What's the real line between just a really fast fire and a truly devastating blast? What's going on at the molecular level to unleash so much energy so incredibly fast? Figuring that out is the key to understanding, well, everything else we're about to talk about. And to get our heads around it, we're going to break it down into 4 main parts. First up, we'll get into the anatomy of an explosion. Then we'll see how scientists actually measure the power. After that, we'll explore how these things become a tool for every job. And finally, we'll look at the incredible science of how investigators read the aftermath. Okay, so let's start with the absolute fundamentals. Look, whether we're talking about a tiny firecracker or a massive military warhead, every single explosion boils down to one core principle: a super rapid, self-contained release of an enormous amount of energy. You see that keyword on the slide? Self-contained? That is everything. See, a regular fire needs to pull oxygen from the air around it to burn. An explosive? Nope. It has everything it needs, both the fuel and the oxidizer, packed right into its molecular structure. It's basically a complete, violent reaction just waiting for a trigger. And you have to know, not all explosions are created equal. Not even close. This slide shows the critical difference. On the one hand, you have low explosives. They go through something called deflagration, which is really just a super fast burn. Their job is to push. On the other hand, you have high explosives. These things detonate. That creates a shockwave that moves faster than the speed of sound, and its job is to shatter. That's the difference between launching a firework and demolishing a building. And even within the world of high explosives, there's a kind of hierarchy. It's all about a chain reaction. You start with just a tiny bit of a really sensitive primary explosive, like the stuff in a blasting cap. It's super unstable, easy to set off, but that initial shock is then powerful enough to set off the much more stable, but way, way more powerful secondary explosive, like TNT. It's actually a brilliant system when you think about it, a way to safely control absolutely immense power. So we know there are different types, different classes. But how do scientists actually put a number on that difference? How do you measure the power of an explosion? Well, the first, and maybe the most important metric, is something called detonation velocity. Now, this isn't just how fast the fireball gets bigger. It's the almost unbelievable speed that the chemical reaction itself rips through the explosive material. I mean, we're talking thousands of meters or several kilometers in a single second. It's just staggering. And this chart here gives you a feel for just how huge the difference can be. Way over on the left, you've got something like AMPHO, which is a common mining explosive. It's relatively slow. Then way on the other end is HMX, a high-performance military explosive. That massive gap in speed is the difference between an explosive designed to push tons of rock and one designed to shatter solid steel. But it's not just about raw speed. Scientists look at a whole bunch of other things. There's brisance, which is basically a measure of its shattering power. And then there's gas volume, which tells you how good it is at pushing and heaving stuff out of the way. Each one of these metrics tells a different part of the story, and it helps to find what job an explosive is really suited for. And to put all that energy into perspective, get this. Some research shows that the explosive combustion of simple magnesium with carbon dioxide, yep, the gas we breathe out, can release 24.7 kilojoules per gram. That's a higher energy density than TNT. It's just this wild reminder that incredible energy is locked away in some of the most unexpected chemical bonds out there. Which brings us perfectly to our third section. Because by carefully tweaking all these properties, the velocity, the pressure, the gas volume, scientists and engineers have managed to turn these incredibly powerful reactions into precise tools for a mind-blowing range of jobs. And this table just gives you a taste of how diverse we're talking. I mean, it goes all the way from civil engineering, using ANFO to carve out tunnels, to military warheads that use RDX for maximum fragmentation. But it also includes things you might not even think about, like industrial welding, and even the carefully controlled reactions that create the beauty and magic of fireworks.
So let's just take mining for a second. The goal there isn't to pulverize the rock into fine dust, it's to break it and move it. That's why an explosive like ANFO is perfect. It has a lower velocity but produces a huge volume of gas, which is exactly what you want for heaving and displacing massive amounts of material without just wasting energy.
Now, contrast that with the military application. Here, the goal is the exact opposite. You want the most shattering power you can possibly get to break a metal casing into as many high-velocity fragments as possible. And that's why they use materials like HMX, with its extreme detonation velocity, to get that superior fragmentation effect. See? It's all about matching the right tool to the right job. But what happens when the blast is all over? Well, that leads us into our final section, the absolutely fascinating science of forensic analysis, where investigators have to piece together the entire story from whatever is left behind. You know, a blast site might just look like pure chaos, but to a trained investigator, it's actually a scene that's filled with microscopic clues. The whole goal of post-blast forensics is to learn how to read those clues and reconstruct exactly what happened. The process is just incredibly methodical. It's like detective work at a microscopic level. So it starts with collecting these tiny, almost invisible residues from the environment. Then, in the lab, they use advanced analysis to look for the unique chemical fingerprint of the explosive, things like nitrates or specific traces of metal. And ultimately, these tiny little clues can help them reconstruct the entire device. And these chemical traces can tell a remarkably detailed story. They can help distinguish between a commercial explosive, a military-grade material, or a homemade one. Forensic scientists can even detect faint trace vapors in the soil to find hidden landmines, or sometimes they can even trace the raw materials all the way back to where they came from. But let's be clear, this work is anything but easy. As this quote points out, the evidence they're looking for is incredibly fragile. Things like rain, heat, and just general environmental contamination can quickly wipe away or obscure the chemical signatures they need to find. It makes the whole thing a constant race against time and the elements. Which really brings us to our final lingering question. From shaping our world or construction to posing these incredibly complex security threats, explosives represent this powerful duality. And as our understanding of these chemical reactions gets more and more sophisticated, the challenge is always going to be there. How do we continue to harness their constructive power while at the same time safeguarding against their destructive potential? It's a balance that science, engineering, and all of society will always be working to maintain.